Today we will see in detail about the Schrodinger equation, both time-dependent Schrodinger equation and time-independent Schrodinger equation. Several formalism were available to study the quantum mechanics. Among them, two original and independent formalism were those of Heisenberg and Schrodinger. Heisenberg approach is matrix mechanics. The description of a quantum system is expressed through the time evolution of the matrix operator for different quantities characterizing the state of the system like position, momentum, and angular momentum. On the other hand, the Schrodinger version of quantum mechanics is based on the evolution of the wave function characterizing the system at, as dictated by the Schrodinger wave equation. Usually, the Schrodinger wave equation cannot be derived, but it can be postulated and tested, and that postulation is tested against the experiment. Its success then justify its acceptance. In order to guide us in that regard, we can postulate some condition to be fulfilled by the wave equation. There are three important conditions. There are so many conditions. Here we are going to see the three important conditions. That is, the equation should be linear and homogeneous, which is the condition met by the waves in general. So, waves will satisfy this condition. That is, it is linear and homogeneous. Uh, then what is linear? If wave function psi1 and psi2 are the solution of solutions of wave equation, then a1 psi1 plus a2 psi2 must also be the solution. Here a and b are some constant, arbitrary constant. The second condition is we need the wave function at a given instant, that is initial wave function, which will have sufficient information about the system, which is to be sufficient to specify it at any other later time. Then the wave equation must be differential equation of first order with respect to time. Here, I like to highlight one important point. In the case of classical mechanics and electromagnetic theory, we have seen the wave equation, which is second order time derivative as well as second order position derivative. Here, we are dealing with operators. So it must be the first order time derivative. If you know the wave function at initial time, then if you take first order time derivative, you can find the wave function at any other time. And one more important point is in the case of classical mechanics, Newtonian mechanics, basically, F force is equal to F equal to ma. That acceleration is a second order derivative. That is, acceleration is observable quantity. It is second order derivative. Here, you remember that we are dealing with the operator. So that is one important point. Another important point is, so we are taking the first order time derivative, and another important point is, if the wave function were second order with respect to time, then the knowledge of first order time derivative of the initial wave function would also be needed. So let us we are going to take second order time derivative like classical physics. Then in this case, you need a initial wave function, which is the first order time derivative. That is important condition, which will make some complications. So This is our second condition. And the third condition, we require the wave function to conform to pore correspondence principle. You know what is pore correspondence principle? Under certain conditions, uh, the quantum mechanics is analogous to classical mechanics. Remember that this is under but certain condition or limit. So these three conditions has to be satisfied. There are two type of Schrodinger wave equation. One is time dependent and the other one is time independent. Now we will see the time dependent Schrodinger wave equation. First, let us consider the simplest case possible. That is the energy is equal to p squared over 2m. This is kinetic energy. Since it's a free particle, we assume the particle is free, there is no potential energy. So, for a free particle, E is equal to p squared over 2m. That we know. The particle's wave function with Fourier transform in one dimension can be written as here I like to highlight one of the most important points. See, in quantum mechanics, we are dealing with wave particle duality. So naturally, the particle will have specified momentum and energy. This exponent term contain both momentum and energy. This Fourier transformation can be written as psi x of x and t is equal to integral a. This is arbitrary constant, of course, which is a function of momentum times e power I px minus et over h cross tp. That is the integral is over momentum. So here p and e are the particle properties. So if you take time derivative, as I said, this is a first order time derivative. So if you take first order time derivative, what will happen? This you can see here you have minus et over h cross here. I you have I. So I can take minus I over h cross. Here you have minus I over h cross. Integral this E is there. When you are differentiating, you will get E. So you will get this integrand. So now you bring this minus I h cross to the left hand side. This will become minus I over h cross will become just I h cross. So you remember this expression which I have shown in blue color rectangular box. We are, of course, we are going to use it in the later stage. So we have seen the time derivative, first order time derivative just now. Now we will take first order position derivative. Partial t by tx psi x and t is equal to this one. Now you are differentiating with respect to x. Remember that. So naturally you have I h cross plus I h cross and you have P here, P and the rest of the integrand will come over here. Uh, Here we are going to take second order position derivative. The reason behind it, only the second order position derivative will give you the energy. That is, here we are using as an operator. So this will give you actually p squared over 2m. So p squared over 2m, we have to get p squared over 2m. What I am going to do is I am taking again the derivative with respect to x. That is second order derivative. In that case, I will get I over h cross again. I over h cross into I over h cross will give you I squared over h cross squared. So that is I squared is minus 1. Minus 1 over h cross squared. Here you will get p. Already p is there. Second time if you differentiate, you will get p squared. So you divide it by 2m. Now you can understand why we are taking second order partial derivative. So we are taking first order position derivative. For that I have explained the reason. Now I have also explained the reason for why we are taking the second order position derivative. Yeah, that is in order to get the energy p squared over 2m in order to get the kinetic energy. Now you bring this minus 1 over h cross squared this left hand side, you will get minus h cross squared over 2m uh, t2 over tx2 psi x t, which is equal to integral p squared over 2m, and this integrand part will come. So this also I am going to take now in order to solve the problem. Earlier we have seen the first order time derivative. Now we have seen the second order position derivative. Now we have seen these two expressions. This is first order time derivative. This is second order position derivative. Now subtract this from this. So 1 minus 2. So this will become in the left hand side I h cross delta over delta t psi x and t, plus this minus of minus will become plus h cross squared over 2m delta 2 over delta x2 psi x and t. Uh, in the left hand side you will get e minus this p squared over 2m, then the rest of the integrand part. Now, by definition, we have started with free particle. For a free particle, E is equal to p squared over 2m. So that means this term will become 0. So naturally, the total integrand will become 0. Then if you bring this second term to the right hand side, you will get minus h cross squared over 2m delta 2 over delta x2 psi x comma t. So here in the left hand side you have I h cross delta over delta t psi. So we have arrived with this expression. This equation will satisfy our earlier three conditions. That is a very important point. Linearity condition, first order time derivative, and pore correspondence principle. It will satisfy all the three conditions. Now, uh, assume a particle is not free, then E is equal to P squared over 2m plus V, which is a function of x and t. This is the potential energy. In general, Vx of t is independent of time. According to inverse square law, you can give. Generally, it will be taken as independent of time. And here we are considering that it depends on time. Because this potential is independent of time. Uh, Unless a force act on it. So if force act on it, then it will be time dependent. So this will be if you add this potential also, you will get I h cross first order time derivative of psi minus h cross square over 2m second order position derivative of psi plus v x and t psi x and t. The above equation, this equation is called time dependent because it depends on time. Time dependent Schrodinger wave equation. So this is the time dependent Schrodinger wave equation in one dimension. In three dimension, the delta 2 over delta x2 can be replaced by the Laplacian operator del square. So except that, no change here. From above, we can come to the conclusion that the energy operator is equal to IH cross delta over delta T. Here, IH cross delta over delta T. If it act on psi, it will give the energy E. That is the meaning of this one. Similarly, the P is equal to I minus IH cross del. So if you square it, minus of minus will become minus, the squared will become plus, and I squared will become minus, and minus 1. I squared will be minus 1, and this will become h cross squared del squared. So h cross squared del squared you will get. So this is equal to minus h cross squared del squared. That is square of the momentum operator. So now you can understand why we are taking first order time derivative and second order position derivative. So here we are dealing with the operator. Energy operator is equal to I h cross delta over delta t, and momentum operator is minus I h cross delta. So the wave function is used to find the probability of finding the particle at a small volume TQR. That is the probability density P multiplied by TQR small volume is equal to modulus I squared TQR. If you integrate between minus infinite to plus infinite, the modulus I squared T, TQR must be equal to 1, because you must find the particle somewhere in the region. So it must be equal to 1. We also add the following property. This is called pawn inter. This is also sometimes called as pawn interpretation. Anyway, I will explain that using diagram in my next slide. It must be finite everywhere in space and through time, in order to yield the sensible prediction on the probability, because it must be a finite values. The probability is varies from 0 to 1. The minimum value is 0, maximum is 1. And also it must be single value in order to be physically unambiguous. Then third one is the wave function and its derivative must be continuous whenever the potential is finite. So when potential is finite, wave function and the derivative must be a finite one. So uh, finally, the fourth condition is the wave function must tend to zero at infinite. Just now we have seen some of the properties of wave function that is interpreted by the Born. Born interpretation of wave function is it is a single valid one. You can see this first diagram. It has a different frequency and a different amplitude. But however, you have single value, unique value at a particular position. So this is single valid one. You can find the definite value from this diagram. So it is a valid wave function. Then you come to this side. See, at this particular point, you have two values. If your wave function is like this, you have two values here, here also two values. So this is not an valid wave function. So you can ignore this. Similarly, here you come. Here it is a continuous one, not only continuous, wave function is continuous and its derivative also continuous. This is the wave packet. Wave function and its derivative is a continuous one here. So this is valid wave function. This is valid wave function. If come here, here there is a discontinuity, here there is a discontinuity. Here it is zero, of course. See, In case of momentum, you are going to take a second order derivative. Even at first order derivative is infinite here. Here infinite, here infinite, here infinite. So this is not a valid wave function. And come over here. Here there is a discontinuity. If you take first order derivative, it is infinite. Then the second order derivative is questionable. So it cannot be a valid wave function. So here this and this is a valid wave function. So far, we have seen the time-dependent Schrodinger wave equation. Now we will see time-independent Schrodinger wave equation. For that, we are going to separate out the variables. See, this is the total wave function psi, which depends on x and t. I am going to separate this as pi and f. Pi depends only on x, f depends only on t. Substitute the above equation in time-dependent Schrodinger equation, and for a conservative system, potential is independent of time. So I have written this as Vx. There is no t dependence. The reason I have already explained. So I replaced psi pi pi f, pi f, pi f. So now you can take this pi in front of the derivative because it depends only on x. So delta over delta t ft will become. In the right hand side first term, it depends is a second order position derivative. So only pi is a function of x. So you can bring ft in front of this derivative. So you will get ultimately this expression. Uh, then we will reduce this expression further. So we got this expression finally. Now you divide this by pi f. So in the first term, pi will cancel out. You will get only 1 over f of t. And here you come in the right hand side. F of t is here. So f of t will cancel with f of t. You will get only pi x when you are dividing by pi f. Pi which is a function of x. Uh, then here in the second term right hand side both will get cancelled because we are dividing by pi f. So finally you will get only this expression. Here if you go through it carefully, in the left hand side you have terms which contain only time dependence part in the left hand side. In the right hand side, you have only position dependent part. So both are totally independent. If you change the time, nothing will happen to right hand side. If you change the position, nothing will happen to the left hand side. So both will have a common constant. That common constant is E. So I am replacing this by E. That is left hand side by E. So then this will become minus h cross squared over 2m 1 over pi delta 2 over delta x2 pi x plus v of x, which is equal to E because I have replaced this as E as a common constant. So finally, we arrived with this expression that is minus h cross squared over 2m 1 over pi delta 2 over delta x2 pi plus v of x, which is equal to E. Now you multiply the above equation by pi. So this pi will get cancelled. Then v pi of x and E pi of x. The above equation is called the time independent Schrodinger equation. See, there is no time dependent here. All are position dependent. So, in three dimensions, same thing can be written as delta 2 over delta x2 can be replaced by Laplacian operator del square. So this is for three dimension. In three dimension, it can be written as like this. So this is called time independent Schrodinger wave equation. Thank you very much for watching my video and supporting me continuously. Thank you very much.